Okay, define and use radians and the exact values. 4J this is. Alright, you'll notice that I kept my very pretty picture because it's a pain to draw a nice circle. So, ultimate goal of today is unsurprisingly to define what radians are so that you're happy with those, or at least content, and exact values. So, first things first, radians. Now, I'm going to open this by asking a question that unsurprisingly doesn't have a good answer. How far around is it in an angle all the way around a circle? Okay, great, that's 360, good job. Kind of learnt that in primary school. Bit boring, why are you asking? Well, I'm so glad you asked about my asking. So, I've got 360 all the way around, but why? Why 360? That's weird. Like, that's a pretty specific number. Why not 100? Or why not just 1? And then we go, okay, I go once around the triangle, and then, once around a circle, then I can chop it up into bits. Why 360? Turns out that that's got a history going back to Babylon and all the rest of it. They liked having things to be divisible because they really sucked with fractions for a while. So they went, you know what, if we pick 360, that means we'll be able to divide it by a lot of numbers, and then if it's somewhere in between, we'll just let that go, and then we'll say, oh, it's exactly this many. So that's basically why. And then eventually they decide, oh, actually, we kind of need to be more accurate, so we'll come up with arc minutes and arc seconds. Great, so now you've got essentially a whole lot of fractions. Good job, isn't that what you were trying to avoid? So, let's not do that. Let's go back to basics and go, hang on, 360, we just make that up. Chuck it. Right? I don't want 360. I want something that actually mathematically makes good sense. How far around a circle is it? Well, that'd be the circumference because I'm going around a circle. Specifically, how far around a unit circle is it? Well, okay. Well, around a circle is 2 pi r, the circumference, okay. Well, this thing has r as 1, so it'd be 2 pi. So, I'm going to give to you, this is now 2 pi, and our units, since we base it off the radius, is c for circumference. So, degrees has the little o, radians has a little c. That's way too big, but if I write it this small, it's going to be a little bit hard to see. Pun? Okay, so it's 2 pi all the way around. Unsurprisingly, this is also 0 as well. So start at 0, go all the way around, that's 2 pi. Okay, fine. So if we only went halfway around, half of 2 pi, that'd be pi. So pi radians. Alright, if I only went a quarter of the way around, well that'd be half of this, so that's pi on 2 radians. Okay, great. If I went 3/4 of the way around, it'd be 3 lots of that, so that's 3 pi on 2 radians. Now, if you don't like fractions, suck it up, because they're in math, and you're going to love them, or you're going to leave. That's the basic gist of how this is going to work from now on. So, okay, that's what radians are. If you desperately want a conversion, fine. You take whatever you've got in degrees, divide it by, oops, where's my colours? Got red, why not? Divide that by 180, and then times by pi, and that will equal radians. Actually, why did I change that? Hang on. Oh, sorry, pi. There. Now, why does that work? Because you're going, okay, degrees, I'm going to divide by, imagine it's 360 and 2 pi for a second. Divide by 360 tells you how far around the circle you are. Times by 2 pi, well that just puts it back around the circle, just you've switched units. So that's why that works. Most of the time, you don't want to think about that. Most of the time, you just want to be starting and ending in radians. Having said that, the book's going to start everything in degrees because it treats you like a child. So you're going to have to deal with that for a little bit. But for a lot of you, that'll be a nice security blanket, but I'm going to rip the security blanket off you before too long. So prepare to be in the mathematical cold until you learn to embrace it. Okie dokie. So, that's radians. What I'm more interested in is exact values. By the way, the reason we're going to change all this to radians is so that when we do calculus next year, it actually works out easier. Because if you stick around with degrees, you end up with a horrible number of extra, not variables, extra constants spitting out everywhere, and it just makes the math ugly. Whereas if you use radians, it's like, nice. Okay, so I want to fill in this table. I want to know what sine of 0 degrees is, sine of 30 degrees, sine of 45, sine of 90, sine of 60, sine of 90. Great, well, first thing I want to do though is actually not be a child and turn this into radians. So 0 is still 0. If we go over to this, 90 is pi on 2. Okay, I want to fill in the rest of these. So be a little bit smart. All right, 45 is half of this, half of the half would be a quarter. Okay, 30 is a third of that, so a third of the half would be a sixth. Cool. 60 is double 30, so this will be double that, so 2 pi on 6 or pi on 3. Hey, look at that, aren't those nice numbers? Almost as though this stuff works out if you do the math the way that nature intends, rather than, oh, I'm just going to slap the 360 in there and see how it goes. Alright, so we need to figure out what these angles are. Now we could draw these and measure them and, oh yuck, you'll get terrible approximations. The steadier your hand is, the better it'll be, the better your ruler is, the better it'll be, but it's never going to be quite right. We're in math, we like precision, perfection, loveliness. So, I've got me here some triangles. Now, I've got double markings on all of that. That would be an equilateral triangle. On this guy, these two sides are the same. It's a right angle triangle. This is going to be an isosceles. I'm going to exploit what we know about these to fill in this guy. So, first things first, I know this is an equilateral triangle, therefore all the angles have to be equal. The triangle has to add up to 180, therefore this has to be 60 degrees. Okay, fine. I'm not a child though, so we're going to change this into pi on 3. Okay, it's the same on all the corners, great. Well, at this point, that's a little bit fiddly because I don't have any right angle triangles. Until we go, oh, hang on there. What if I cut that in half like that? Oh, very good. So, we'll take a look at that and go, oh yeah, that's actually a really good idea. Because now, I have a right angle. How helpful. Well, that would mean that this guy up here, 90, 60, therefore the remainder has to be 30, or if I'm not a child, pi on 6. Okie dokie. Well, I'd have to give these some lengths so that I could do anything with it. So I'm going to pick this to be 2 and this to be 1 because I've halved exactly. Now I could pick 1 and half here, but I'll keep them as full numbers just because it makes life a little bit easier. Alright, well what's this last third side? Well, it's a right angle triangle, so I could use pi tag. Okay, 1 squared plus something squared is 2 squared. Well, that's 4 after you square it. This squared is 1, so the missing thing is 3 after it's squared, so this must be root 3. If you're not happy about that, take a second, just solve it yourself. You should get root 3. Technically we'll get plus minus root 3, but we're going to say all of these sides are positive for now. Okie dokie, so we've got this. Okay, fine. Well, what does that tell us? Let's see. Sine of, where are we going to start? Oh, we'll start at 60, why not? Sine of 60, so sine of pi on 3. Okie dokie. Sine is opposite over hypotenuse. So opposite over hypotenuse. Root 3 on 2. Okay, fine. What about cos? Cos of pi on 3. Okay, cos of pi on 3. Cos is adjacent over, for this one, is adjacent over hypotenuse. Well, that's 1 on 2. Isn't that pretty? Well, we can use this guy as well. Sine of pi on 6. Sine of pi on 6, O over H. And cos pi on 6. Okay, where are we? Pi on 6 is A over H, root 3 on Q. And cram in tan down the bottom. Tan pi on 3 is root 3 divided by 1, but to divide by 1 cancels out. Tan pi on 6 is going to be root, no, hang on, 1 on root 3. There we go. Cool. Now, 1 on root 3, that's a little bit ugly. Dividing by root 3 is not so crash hot. Well, if I times the top and the bottom by root 3, if I times the top and the bottom by something, that's fine. It's just an equivalent fraction. I get root 3 over root 3 times root 3 is 3, so root 3 on 3. Either is fine, 1 on root 3 or root 3 on 3. They're equivalent. this is going to turn out to be a bit more intuitive shortly. Yes, good. So that's all that triangle done. We've used up all the angles. Cool. What about this guy? Well, we said that this was an isosceles. Well, if that's 90, these two have to be the same since they're isosceles. So this must be 45, this must be 45. However, we're not children anymore. Pi on 4, pi on 4. Beautiful. Alright, well I can have this be any length I want, so I'm going to choose 1 and 1 to make my life a lot easier. Okay, I need this last length. Okay, so this guy squared plus this guy squared is this thing squared. 1 squared plus 1 squared equals 2. Square root of that, root 2. Beautiful. Alright, sine of pi on 4 equals O over H, gives me 1 on root 2. Similar argument to here, times the top and bottom by root 2, get root 2 on 2. Good. Cos pi on 4, same story, look at that, everything's the same. Take your time to think about it if you're not happy about it. And 10 pi on 4 is O over A, which is 1 over 1, which unsurprisingly is 1. Beautiful. Okay, so we've done all this work, great. Well, now we can fill in our table, or at least the middle chunk of it. Okay, sine of pi on 3 is root 3 on 2. And feel free to jump ahead of me. Putting all these into there, eventually you'll end up with in fact, I'll write this both ways. Just now, just so we can make an observation later. Beautiful. So we filled in a fair chunk of the table. Fantastic. Isn't that pretty? Alright, well, what about these last guys? Well, go back to last time, and we said, well, sine theta represents how tall this triangle is. Alright. As I make this triangle taller and taller and taller, this blue line is going to get closer and closer to that height. And once I go past there, it gets smaller. But what I care about is at exactly 90 degrees, or more accurately, pi on 2 radians, how tall is that line? Well, it touches the point 1, so it must be exactly 1 tall. So this is 1. Yes, I've deliberately left space. Okay. What's cos doing? Well, as this gets taller and taller, cos was the width. So it gets skinnier and skinnier and skinnier until, well, there's nothing left. So, big fat 0. Alright. Well, oops, wrong side. 0. Okay. Okay, well, what happens if I go the other way? Because now I want to approach 0. Okay, so as this thing gets flatter and flatter and flatter, what's happening to the height? It's getting smaller and smaller until it's gone. None left. Similar story, what's happening with the width as I get wider and wider and wider, or lower and lower, I get wider and wider. We go to 1. Cool, go to 1. There we go. Beautiful. Alright. Fantastic. Which way will I do it? I'll do it this way. Cool, okay, thinking about tan from before, is way up here. As I get smaller and smaller and smaller, that tangent line gets smaller and smaller, so he's a big fat 0. What happens as I get bigger and bigger and bigger and bigger? Well, this is getting bigger and bigger, but hang on. If I get to here, how do I have tan? No, this doesn't touch this anymore. My dotted line can't ever reach it because they're parallel. Is it infinitely tall, or what's going on there? Well, this is a little bit sus, so we'll leave that blank just for now, till we have another thought. Okay. At this point, we're almost done. I've got 0, half, root 2 on 2, root 3 on 2, 1. Okay, fine. Well, this is a lot of stuffing around to just fill in this table. Well, maybe I can be a little bit smarter and just remember the table. Just like how if I ask you, 5 by 6, you should just be able to go, well, that's 30. Thanks for asking. You're not going 5, 10, 15, 20, 25, 30. You're not taking that long anymore because you're not a child. So, I don't want you to be a child. Time to grow up. I need you to memorize these. Now, that might sound like it sucks, but back in year 3, it also sounded like it sucked when you had to remember your times tables, and back in like years prep and 1, where you had to remember, 2 and 3, that makes 5. You started this stuff, right, but 2, 3, 5, done, let's go. Right, we need to get fast at this so we can actually do something useful with it. Now, this looks like a jumbled mess currently, but I present to you the following. If I take the square root of this, and the square root of this, and the square root of this, 0, 1, 2, 3, 4, and they're all square rooted over 2. Square root of 0 over 2, 0 over 2 is 0. Great. Square root of 1 over 2, that's just 1, half. Square root of 2 over 2, square root of 3 over 2, square root of 4 over 2, that's 2 over 2 is 1. Brilliant. 1 down, 2 to go, okay. Well, hang on, this thing, 1, 1, root 3, 2, root 3, 2, root 2, 2, root 2, 2, root 1, 2, root 1, 2, root 0, 2, root 0, 2. These are the same thing, just backwards. Brilliant, so I don't even have to worry about that. So, 1, 0. Fantastic. Alright, last one, oh hang on, I've got a 0, I've got a root 3 on 3, and then a 1, and then a root 3. If you want to try for it, one way that you can do is say, okay, this is 0 lots of root 3. So it's root 3 times 0 on 3, and then root 3 times 1 root 3th, then root 3 times root 3th, and then 1 times root 3. But that gets a little bit clumsy, so I'm going to suggest that you don't. Instead, and also it stuffs up at this point. So instead, I'm going to suggest you do the following. Remember from last time, we're going to put it over meow. Tan theta equals sine theta over cos theta. So tan equals sine divided by cos in short. 0 divided by 1, 0. A half divided by root 3 on 2. Fiddle with your fractions for a little bit, and you'll get root 3 on 3. Sorry, you'll get 1 on root 3, which you can then rationalise to root 3 on 3. Root 2 on 2 divided by root 2 on 2, something divided by itself, 1. Root 3 on 2 divided by a half, play with fractions, you'll end up with root 3. 1 divided by 0, well hang on, that's not 0, it's not 1, and it's not infinity. Don't tell me it's an infinity, that's not a value, it's a concept. So, how do we deal with this? Whenever you divide by 0, undefined. Right, so, there's reasons for this that we'll get into very shortly, but whenever you divide by 0, it is undefined. You can have meaning to what it means, but by default, it's undefined. Cool. So, I will get rid of this bit now, just the safety roots. That says, it's gone. So, everything you see there in this table, I need you to memorise. You've got about a week to memorise it until it becomes really problematic, because if you don't memorise it, everything you do is going to be super slow. And if you're just constantly flicking to the back of your book to look at it, you'll never remember it, just like your times tables. If you have to constantly look at them to remember them, you're not actually remembering them. Force yourself to remember. It might take a little bit of practice, but you'll get there. It's not that bad. You had to remember your 12 by 12s. Now I'm asking you to remember 3 by 5. Not that many. And a whole bunch of them are easy, zeros and ones. Beautiful. So that's what I need you to learn by next time. The thing that tells you that this is not infinity, for those of you that will be screaming at me, but I want this off to infinity. So this does, as you go bigger and bigger and bigger, getting closer to 90 degrees, it does go up higher and higher and higher and higher and higher. However, we remember from last time that in this quadrant, tan was negative. So when I switch over from, say, 89 degrees, very positive, through to 91 degrees, it's all of a sudden very negative. But if it went off to positive infinity, right, shouldn't it come back down from positive infinity? So that's why this thing's undefined, because at that point it switches from all the way up at the top to all the way down at the bottom. You can think about it as cycling around a universe if you want, fine, I don't particularly mind, just as long as you know that at that 90 degrees, the pi on 2, you've got troubles, undefined. Beautiful, 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 beautiful. I think that's it. Yes. Cool. So that's for J. It is not the hardest thing in the world, but... Oh, now. we also have to do things of this nature. What if I have, say, 5 pi on 4? Okay, well, we've got a little bit of an issue here. So what we do, we draw a crappy unit circle, doesn't have to be good at all. And we decide, okay, where is 5 pi on 4? Alright, well, pi on 4 was 45 degrees, 2 pi on 4 would be straight up, 3 pi on 4, 4 pi on 4, because that's pi, 5 pi on 4 would be down there. Brilliant. Next stage, writing your ASTC. Cool. Is sine positive or negative here? Well, only tan is positive here, so this must be negative something. Sine of, what was the original basic angle in here? Oh, actually I won't put that there. Alright, forget that. What is this angle here? Call that the critical angle for short. That's pi on 4. That's pi on 4. Beautiful. Alright. Negative sine pi on 4, sine pi on 4, root 2 on 2. Beautiful. Okay. What if we have something a little bit different? Cos of, say, 5 pi on 3. Okay. Stage 1, draw a crap unit circle. Okay, 5 pi on 3. Alright, well this is, remember that's 0, that's pi. Okay, so that'd be 1 pi on 3, 2 pi on 3, 3 pi on 3, 4 pi on 3, 5 pi on 3 must be down there. Cool, so we're in that quadrant. That's in the quadrant C. So this would be a positive since cos matches. The critical angle is how far it needs to go to get back to the horizontal. So critical angle would be pi on 3 because 5 pi on 3 plus pi on 3 would be 6 pi on 3, otherwise known as 2 pi. So this is cos pi on 3 now. Positive cos pi on 3, we go over to our table and we get positive 1/2. Cool. Tan of, what are we going to do? 3 pi, no, let's pick something better. What have I not used? 6s. And we'll go, oh, yeah, we'll do that, that's a good one. Okay, so 9 pi on 6, alright, first thing we do, or a crap unit circle, alright. So I've got 6 pi on 6 would take me all the way over to here, so that's pi, and then I need 3 pi on 6 more. Alright, well 3 on 6 would be half, so I'm half more of a rotation. So I'm down here somewhere. Alright, what's the angle to get back to the horizontal? Well, that's pi on 2, but I could describe this as either pi on 2 that side or pi on 2 this side. So that's a little bit weird. Which thing am I in? Oh, well, tan's over here, cos is over there. Well, hang on, I'm halfway in between positives and negatives. How does that work? That's a little bit weird. Well, our answer comes in the form of, what's tan of pi on 2? That's undefined, and this is why. We've got these troubles of it's simultaneously flicking between positive and negative. We know that it's not 0, so it has to be undefined. Yeah, okay. We'll go a couple more just for examples, because this can get a little bit weird. We'll do that and we'll do that, okay. Pick something, let's say 2 pi on 3. Cos of, say, negative pi on 6. And tan of 17 pi on, there we go. Do this turned on by itself, that's not weird at all. It sounds like it's about to die. But anyway, cool, alright, sine of 2 pi on 3. Crap unit circle. 2 pi on 3. Alright, this is 0, this is 1 pi. I need 2/3 of pi, so that's over here somewhere. A S, TC. Cool, we're in S, they match, so that's positive. how far away am I from the horizontal at critical angle? I need another pi on 3 to get up to a full pi. Cool, pi on 3 for sine is root 3 on 2. Again, you type this into your calculator to check you're doing it right, but the whole point is you do this without a calculator ultimately, because basically we have to get there by then. Cool. Next one, cos of negative pi on 6. Well, hang on, how do you have a negative angle? Remember way back when we said positive goes this way, negatives go that way. So we're going backwards, pi on 6, that's about there. A, S, T, C, it matches, so it's positive. And then we're just thinking, how far away from that are we? From the horizontal, well, that's pi on 6, because that's how far we travel. Cos pi on 6, root 3 on 2. Last one. Cool, grab the unit circle. 17 pi on 4. Oh, hang on, that's quite a lot. So I've got 0 pi on 4. Over here is 4 pi on 4, because that's a full pi. Over here, 8 pi on 4. Over here, 12, 16. Okay, and then one more, so I'm up here, 17 pi on 4. Everything is positive there. So we've got positive, and then 10 of critical angle. Cool. So we did laps. So this was 0 pi, single pi, 2 pi, 3 pi, 4 pi, because 4 was 4, 16 pi, plus one more pi on 4. Cool. So we've got one by looking at the table. Beautiful. Now, I am fully expecting to get questions on this because it's moving from degrees to radians and then using them to do some weird little calculations. I'll see you on Monday and hopefully we'll have a bit of a chat for anything that gets lost. I promise you it is not the hardest thing in the world, it's just a little bit tricksy. Anyway, that's 4J. Best of luck to you.